briefly, and then we'll go. Right, so welcome everyone. Let's get started. Today's seminar, Cyber Physical Systems Seminar. It is my pleasure to introduce you to Professor Riccardo Sanfelice, and he's now a professor of electrical and computer engineering at the University of California, Santa Cruz. And he got his master and PhD both from the University of California, Santa Barbara. He's now actually the director of the Cyber Physical Systems Research Center at UCSC. He's interested in modeling, stability, robust control, observer design, simulation of nonlinear and hybrid systems, so the mathematical foundations of cyber physical systems, with applications ranging from robotics, power systems, aerospace, and biology. Ricardo has been awarded with several awards from both for actually teaching, education, and research, including the SIAM Control and System Theory Prize, as well as the Best Paper Award from the Control System Magazine, IEEE Control System Magazine, Outstanding Paper Award. With that, please join me again and welcome Ricardo to the CPS seminars today.
Thank you very much for the invitation, Pierluigi, and for everyone that organized this meeting. I wish I was there with you in the same room, but as we know, that is not possible. So I thought I would start my talk. And maybe as many of you, I've been sitting through many talks over the past year, and not because of the speaker, but because just sitting there and not talking to anyone is a little bit not boring, but not very exciting. But so I thought I would start with some picture here of what our campus looks like if you've never been to UC Santa Cruz. And when I was a student at UC Santa Barbara, I didn't get a chance to come. So when I first came here 6 years ago, I was impressed. So this is the view that we have from our backyard. And it's interesting to see that there are trees that are standing still, even after the fire that we have this past summer. There is a lot of exciting trails and a lot of exciting outdoors that these days is pretty much empty. That brings me to my question that I like to start the talk is, you know, many of the students in the audience might probably have an answer to this. So I'd like you to think about this for a second. So what comes to mind when someone tells you hybrid system? Yeah? So maybe you have thought about this because you probably saw the title of the talk, but we want to describe dynamical systems that are hybrid in this talk. We want to focus on systems that have, in particular, two types of dynamics. That's essentially the simple answer to this question. And there are many ways to do that, but there are many applications associated to these systems. Here is one of them. Here are multiple agents. This could be fingers, robots, vehicles that move in a space unconstrained, and all of a sudden they find an object to make contact with. They happen to want to make the contact at the same time so that the object doesn't move around. And moreover, when the contact occurs, there is some change, either of the physics or the controller, and typically both. So basically what happens here is there is an algorithm that is capable of steering the vehicles or the agents to this object. Maybe they know where to make contact. And once the contact is established, there is an algorithm that will now, let's say, regulate force. So you can think about this as a trivialized version of grasping. Actually, this is what it is. There are systems where these transitions are a little bit more abrupt and one needs to cope with those transitions. Here is an example of actually an application that we have in our lab. This is a juggling apparatus developed by Brad Payton at UC Santa Barbara launch point. And what you see here is a ball that moves on this speed rail. The ball has a hole, and there is a piston that is able to impact the ball when the ball is in its neighborhood. And there is one of the lights there, the green light that is beeping, essentially every time that there is an impact. And at that impact, what happens is that the energy of the system, particularly kinetic energy, changes very rapidly. So what we actually do, following the physics literature, is to model the transition as an instantaneous change. Physically, there is no instantaneous change. There is a deformation. There is a transition of energy. There is a PDE associated to that impact. But we don't model that for the purpose of control because we would like to have a very simple model that then feedback will compensate for any uncertainty. In that model, in that system, you have dynamics that are in between the impacts, typically described by a differential equation, continuous time system, if you will. And every time that there is an impact, there is instantaneous change on the state, which is, again, the abstraction of the model. And that creates a combination of continuous and discrete. And actually, the plant you want to, in this case, control is of hybrid nature. Okay? There are other problems that we are excited about, and we work in the past, and this is one other. My background is in electrical and computer engineering, and this is a building block for many of the systems that we use these days. This is an inverter. It actually changes continuous type voltage to alternate voltage. And the way that this happens is by changing the position of these transistors, typically IGBTs for high energy systems. And the idea here is to actually create almost like a sinusoidal signal, which is pretty good enough for powering most appliances, let's say. And the catch is that we don't have a particular configuration of these transistors in a steady state that will create that sinusoidal signal. So what one ends up doing is to having to recurrently switch these transistors in order to create some sort of pseudo-sinusoidal signal. Here you see animation of our control algorithm, which is hybrid. The reason that it's hybrid is because the current and the voltage of the circuit, of the filter, the output of the circuit, is what we want to regulate to almost being sinusoidal. And every time that this quantity, which is a planar quantity, reaches one of these surfaces that are in green, then a switch occurs. So essentially, there is a lookup table behind this that says, if it hit on the first quadrant on the inner boundary, then this should be the new configuration of the transistors, and the other way when it hits the outer. And then, as you can imagine, there is a map between each possible point in the surface to a possible configuration of the circuit. That leads to a closed loop system that is hybrid because of the control algorithm. The plant itself, you can model it as a switch system, and I will talk a little bit more about this later. But it's essentially a non-smooth continuous time system, but with the controller, it becomes hybrid. The good news is that with this type of controller, one can regulate, unlike in PWM, the precision of the generated trajectories, the generated sinusoidal signals, and also know somehow a relationship between precision and the switching rate of the circuit, which is critical for the longevity of the computer. These are the type of hybrid systems that I want to display. I will display several more in the context of robotics as well. But let me say that there are many ways to model this type of systems, and you might be familiar with them. Hybrid systems emerged many years ago in the late 70s, mid 80s. People start combining physical models with models that come more from computer science, like finite automata and transition systems. And that led to great work on what is called hybrid automata, where we have different modes of operation for a dynamical system, transitions between those modes according to conditions that depend on the state. Hybrid systems also appear in the context of optimal control. Most optimal control problems require a control input that is non-smooth. For instance, the problem of steering the double integrator to the origin, well-known problem. When you want to solve the problem in minimum time, then there's a bang-bang type of controller. And there is a state space reformulation of that controller that leads to a non-smooth system. Systems with impacts leading to general measure-driven differential equations, systems with unilateral constraints are also systems that have promoted the use of hybrid machinery to understand, in particular, these rapid changes in the state, which are approximated or abstracted with a discontinuity or a jump of the system. In our work, and I should have said, and I had it on my first slide, this is work that I'm going to present with many of my collaborators, including Rafael Goebel, Andy Till, and Berk Altin and Mohamed Maganem, who have been working with me for many years. And this is summarizing some of the advances and also presenting some of the challenges. And as I said, I will try to sprinkle with as many applications as possible to make it more amenable to this format. But if you are looking at hybrid systems, when we started working on this back in 2005, one of the things that we really wanted to do was to make hybrid systems look like what we know in control theory, which is we tend to believe we know quite well how continuous time systems evolve and how to analyze them and how to design them using control theoretical tools and also discrete time systems. So can we exploit what we know for those type of systems, in particular Lyapunov theorems, Converse Lyapunov theorems, safety, and the such, to actually model hybrid systems and then endow them with those nice properties. So if you're familiar with continuous time systems and you're given a system on some state space, trivialized here by this little ellipse, Rn, and you give an initial condition, then you expect that the trajectory or the solution to the differential equation, if you will be given by a curve that is parameterized by ordinary time t, and that you can draw without lifting the pencil. Right? If you're thinking more about discrete time systems, then you're familiar with trajectories or solutions to the discrete time system that are given by a sequence of points. And each of these arrows that are dashed is indicating a transition from one state to another state. And that transition typically is governed by some sort of difference equation. Okay? Now, if we're thinking about a hybrid system, we are again in some sort of Euclidean space and initial condition given to us. Then what we would like to do is to capture trajectories or again solutions to hybrid systems that are combining the continuous evolution and the discrete behavior. Okay, so what you see right here is a solution of a hybrid system that it starts from this point and then evolves continuously for some time. Then it exhibits a jump or a discrete transition. Maybe it's a change of mode. Maybe it's a reset of some variable to some new value. And then from there, there's another period of continuous evolution, and that keeps occurring. Maybe there is a minimum time over which the continuous evolution occurred, but maybe not. Maybe there is a consecutive transition one after the other, as you see right here. And that could be triggered because of a finite state machine that changed consecutively. This type of behavior appears when we model continuous variables of a system and also variables that evolve discretely, like for instance, logic variables or timers that we reset to trigger certain events in time trigger type problems. They also appear when the dynamics change abruptly, maybe because of changes in the environment. All of a sudden, we want to change the new mode of operation, or because of control decisions, or maybe because of faults, right? All of a sudden, some of the dynamics of the system change, and then you need to reset your state to a new manifold where the new system, maybe under some fault, is operating. Okay? And the way we proceed to understand these systems is to use systematic tools from control theory. We would like to model them. So this is all model-based. We want to analyze them using mathematical tools to get formal guarantees. Certainly, those go to some dimension, right? The limitation is how tractable the problem will be in terms of the size of the model and the complexity of the model. And more, we've been doing work on validating these systems or these results using simulation and also using experiments. So over the years, we've been working on both non-autonomous and autonomous hybrid systems. We started with, the case with no inputs, autonomous hybrid system. We wrote this article with Rafael Gobolen and Detail on IEEE Control System magazine, where you can find a tutorial introduction to this material. Then in 2012, we wrote this book on stability and robustness, of course, modeling as well, of hybrid systems in closed loop form. And more recently, I worked on a textbook that appeared actually last month on how to design hybrid control algorithms that are for continuous time, discrete time, or hybrid plants using tools in the context of control Lyapunov functions, backstepping, and forward invariance for safety, temporal logic, and the such. So I will try to introduce some of all the tools that we develop in this pieces of work. But as I said earlier as well, I wanted to also give you some of the applications, and those are brought to you thanks to simulations that we do using our toolbox for simulation hybrid equations, hybrid systems that we develop in MATLAB. So now we can go back to this question. and think a little bit about more mathematically and based on my introduction, visualize a little bit how we can model them. What will be a mathematical description? And again, mathematical models are useful. People say that all of them are wrong, but some of them are useful. So having those is important for analysis. Here is a model that we use. This is the simplest version of our model. We end up with a model of a plant, a system we want to control. So we have a state, call it Z, and we have an input, call it U. And the state of the system changes continuously in what we call the flows, which are the blue trajectory pieces, according to a differential equation. Okay, so given initial condition and input, you can reason about what would mean to have a solution along the continuous evolution. Every time that there is a jump in the state is automatically instantaneously reset to a new value, and that value is given by some difference equation. So therefore, there's another function right here that determines that, and it's a function of the previous value of the state and of the previous value of the input. Okay, and there might be an output in the context of a plant that's certainly needed because we want to do feedback control for the plant to assign the input. Now, what is very important is to determine which behavior, which flow or jump is allowed at a particular condition, right? There are many ways to do that. The way that we found convenient to develop our work is to say that whenever the state and the input for the plant case belongs to a particular region of the state space and the input space, then the flow dynamics will be allowed. Okay, continuous dynamics of the system can evolve. On the other hand, if the state and the input belong to this other region, then we allow the reset of the state. Okay, these objects have name. The function FP is the flow map of the plant. The CP is the flow set, which is where flows are allowed. DP is the jump set, sometimes called the guard set in hybrid automata. And then GP is the reset map or the jump map that will reset my state. Okay. So now we have a structure, and we will also like to have situations where these functions, FP and GP, might be not necessarily single value maps. They might be set value maps. And one reason to do that is because perhaps I have a parameter in my system, let's say in this juggling apparatus in the context of robotics, where the restitution coefficient is not really known. So I know a range of the restitution coefficient, and I know that one of the components of my state, let's say the velocity, will be reset involving the restitution coefficient. So I could actually come up with a range for that particular value after the jump occurs. And that could lead to an inclusion. So therefore, we can actually change not only for generality of the theory, which is useful for mathematical purposes, but also because of the applications demand this type of objects many times. Another reason that you would like to reason about inclusion is because typically for continuous time systems, we don't know all the dynamics either. So one way to characterize perturbations is to add an inflation to inflate the directions of flow. And that directions of flow will be inflated according to the disturbance. And therefore, you can characterize the perturbation as a set value right-hand side, which will be in this case leading to a differential inclusion. Okay. At the end of the day, if this is confusing, think about it as the velocity of my state being equal to a value or the velocity of my state being taken from a set. That's the only generality that we're looking at here, okay? Which is useful in many problems. Once we have the model, which is a description of how the state is going to evolve, we need to define time and we need to define what we mean by a solution, right? So that's essentially the concept of solution to the system. So because of reasons that are probably obvious by now, we want to separate the effect of continuous evolution and the discrete evolution. In other words, we don't want to have to reconstruct from the time t how many jumps have occurred, or from the time of the number of jumps how many seconds of evolution have occurred. So we want to separate this and make them totally independent. We use two parameters, ordinary time or flow time, t, that is non-negative, and then jump time, j, which is counting 0, 1, 2, and so on, the number of jumps that we have. Okay, you may be familiar with K if you work on discrete time systems, and the reason we use J is because to separate ourselves from discretization. So typically when there is a K, there is a sampling time associated to that. However, in this case, the events might occur not necessarily periodically. So what happens now is that if I pick a hybrid plant, like here, and I want to define a solution concept, then those solutions will be defined on a structure which is now hybrid time. The structure could be as simple for this particular solution that J is equal to 0, so no jumps, and there is flow from time equal to 0 to time equal to T1 when T1 is positive. And then there is a jump, in which case the jump counter J gets incremented by 1, and now I have flow from time equal to T1 to T2 if T2 is larger than T1. And then we can continue over and over constructing this and realize what we call the hybrid time domain, which is an object that is defined on non-negative reals across non-negative integers. Okay. One last observation is that this state Z right here, and we will make some comments about this later, can have variables that corresponds to physics directly, but also to logic, to memory, to timer components, and such properties will become more clear later. But with the structure of the time that we're going to use, which is hybrid, what you can see now is if we are thinking about a scalar system or trivializing the solution to the system at the scalar quantity, we see that if we given an initial condition at time t0, j0, that solution that we see right here evolves continuously for t1 seconds. Then there's a jump, then there's another jump, then evolves continuously and so on. That defines the green set, which is my time domain, okay? What I mentioned earlier was that we are going to use T and J independent of each other because now what you can see here, if you're familiar with continuous time systems, then the solutions that you're familiar with will only evolve for J equal to 0. And it will all go most likely with enough regularity, and your system will go all the way to T infinity, right, in the limit. So you can recover with this time domain structure, discrete time, continuous time systems. You can also recover discrete time systems if you realize that for a discrete time system, T equal to 0 will allow J to go over and over forward in time in discrete time, all the way to infinity perhaps. And surprisingly, or simply enough, if I have a plan of this form and I make the set dp to be an empty set, automatically I'm saying that my plan doesn't have any jumps. So directly I recover continuous time systems, maybe with constraints. And the other way around, if I pick the set CP to be empty, then I recover discrete time systems. In this case, it will be difference inclusions with constraints, but I can further simplify this. Now, with this knowledge in mind, what we can do now is to look at how the solutions will evolve on the state space. So I'm projecting the flow set and the jump set for the plan to the state space. And I can see that for this very abstract choice of these sets, certainly what happens is that there is a lot of overlap. And this solution is a true solution because flows occurs only on the flow set and jumps occur only from the jump set, okay? And the value of the solution is given by a differential inclusion during flows or differential equation if it is an inequality, and the value after the jump is given by the difference equation or difference inclusion after the jump. But you realize as an engineer most likely that this overlap here is a little bit confusing. So in practice, most times we make this overlap to essentially have zero Lebesgue measure. In other words, to just have a little segment where these sets overlap in this picture. Still there, one needs to reason about what should happen on the interface, on the intersection of these two sets. And typically what one does is to create flows in a way like in this picture here, that essentially once we hit the flow set boundary, no flow is possible. In other words, the flow is transversal to the boundary of the condition. Okay, and that what happens in impacting systems. When the ball is trying to hit the ground, the flow cannot exist anymore because otherwise it will go through the ground. So unless we change the model, which will allow flow, then we'll need to trigger a jump. So simulators will exploit that property and be able to generate trajectories like the one I showed you earlier. One of the things that is important is once we have a plant, which might be hybrid, then the controller might also need to be hybrid to solve the stabilization problem. So what we can do is to interconnect them and come up with a general model. And when the whole plant is controlled by a controller and we don't consider perturbations explicitly, maybe just by inflations, but we end up with a closed loop system. And the state of the closed loop system is X, is given by the state of the plant, concatenated with the state of the controller, call it eta. And now we can imagine that we have captured, with some bookkeeping to construct these objects, we have captured the interconnection between a plant and a controller, okay? So when we have some insight of what the controller form should be, PID, observer base, you name it, then we can actually build the structure and then use tools for closed loop systems to design those particular free parameters, right? So Lyapunov based design. These type of domains are typically the ones that we expect in hybrid systems to occur: continuous evolution, a special case of hybrid, not very hybrid, discrete, or again, not very hybrid. But then we have situations where we have maybe, finitely many events, okay? And then after finitely many events, the system solutions evolve only continuously, or the other way around, finite amount of flow, and then the system just evolves discretely. But there's one behavior that is new to these dynamical systems compared to what we know for continuous time and discrete time, which is zero behavior. Zero behavior is a behavior where the amount of flow in between events gets smaller and smaller as time evolves. And as you can see here, as time evolves, the number of events gets larger and larger, the number of jumps get larger and larger, and it happens that this sum converges to a finite number for t. Therefore, what happens is that there is an infinite amount of jumps in a finite amount of flow, and that is characterized by Zeno. Certainly, from a model standpoint for a closed loop system that is based on feedback control, we don't want that because the physics will not be able to evolve forward in time. That type of deadlock needs to be removed, needs to be identified, and needs to be removed from the design of the controller. Before I jump into some examples that hopefully you find related to your research, let me say that hybrid dynamical systems are rich already enough, cover continuous and discrete, as long as they're finite dimensional. Certainly one can generate these trajectories using PDEs, which we don't know yet how to do. But if you're looking at switch systems, we can also model as hybrid hybrid dynamical systems, hybrid inclusions for particular classes of switching signals. We can also model impulsive systems, which typically have a sequence of times at which the impulses are going to occur. We can also model nonlinear system with algebraic constraints. And very importantly, a very popular and useful framework, hybrid automata, we can also model it and encapsulate it in a less descriptive manner, like hybrid automata does, but in mathematical terms, in order to apply the tools that I will provide to you in this talk. Yeah. So a couple brief examples. It's important that we somewhat relate this to concrete elements. So this is a very traditional and canonical example of hybrid systems. Is this juggling apparatus trivialized to where the case of the piston is infinity. It has infinity mass, so there is no control on the piston. And what you see right here is that you arrive to a very natural hybrid system, because if you trivialize the impacts to be a restitution law for the velocity, where this lambda is a restitution coefficient, and this minus is here so that the ball changes velocity and jumps up after the impact. What you see is that Newton's law gives you already a differential equation that is linearly affine. Gamma is the gravity. The events are triggered when the height of the ball is equal to 0 and the velocity is less or equal than 0. This could be strictly less than 0, if you will. And the height doesn't change. So essentially, this creates the flow map, this creates the jump set, and this creates the jump map. And then essentially the complement of this condition will be creating the flow set. And we will actually close that condition. So here are the objects for a plant, if you will, that doesn't have any input, right? So this will be a closed loop system of some sort. And here we see all these objects. We see that these functions here that trigger the behavior are nicely and continuous functions, even though the behavior is non-smooth, as I'm going to show you in a second. A trajectory or a solution to this system that is approximated with our toolbox from an initial condition of high equal to 1 and 0 velocity gives you this particular trajectory. And as you see, there is an accumulation of jumps. We can only simulate up to finite number of jumps, and it's enough to simulate up to 20 to see that the zero time is around 4 seconds. This is the height evolving over time. Again, this is off our toolbox, which also adds the information about the jump. So this is the dashed line that corresponds to the jumps. This is the velocity. The ball goes down, hits the ground, velocity jumps to a positive number, the ball goes up, and then apex time hits the ground and over and over. And here you see the nice non-smooth component of this solution to the system. You might ask why we close these sets. Well, here's what happens. Now consider what I just explained, and now start picking the initial condition, let's say with some energy higher than I had before. So zero time is going to be higher, somewhere around 9.5. I pick a little smaller energy. The zero time is around 6. And as you see, the smaller the energy I pick, the zero time will converge to 0. Okay? So what happens is that this sequence of solutions that I'm picking from a smaller and a smaller initial energy, the sequence is converging to the solution that always jumps in my system. Okay? So to some extent, if I want to develop tools for robustness of hybrid systems, if you're familiar with how the robustness proofs go about, they rely on this very property, which is called sequential compactness. Typically, we forget about this in continuous time systems and discrete time systems because we assume that we have x equal f of x, with f maybe locally Lipschitz, so we don't worry about uniqueness and this type of issues. But when we look at hybrid systems, even though this might be as smooth as you want, this issue might not go away unless you close the sets C and D. So certainly what happens is that, as I explained right here, we need to have some sort of a structural property of the set of solutions, which is in our work, and that's why we work on hybrid inclusions, is guaranteed by properties of the data of the system, which are, for a closed loop system like this, the flow set C, the flow map F, the jump set D, and the jump map G, okay? So that is there. And as you probably realize, there will be some overlap between C and D, and then we will need to embrace non-uniqueness of solutions. So this is what I was trying to say. Similar problems and similar models can be generated for more interesting problems. The juggling problem or the bouncing ball is a trivialized version of things of that sort. But you see here, walking robots, very important area of research, where you have now a nonlinear differential equation coming from Euler-Lagrange equation, typically, and now you have conditions under which there will be resets. It's almost like a dual problem because now you control the physics during the flow period versus during the jumps, like in the juggling apparatus, and then similar kind of analysis can be done for these systems. Typically, one is interested on phase locking or trajectory tracking, and we've done some work on that. There's the emergence, as I said earlier, of logic variables, and this is probably the simplest problem that I can think of where logic variables pop up. This is the traditional control problem of controlling the temperature of a home. We would like to have a temperature within a range, and in order to do that, we will use a heat device to pump energy into the temperature of the room. And one way to do that is to say that Z is my temperature, and Z dot, which is the variation of temperature, is minus Z, maybe some coefficient could be there, plus some parameters. One is depending on the external temperature of the home, and the other one depends on the capacity of my heater. And if Q is equal to 1, it's going to inject essentially energy and raise the temperature. If Q is equal to 0, then the temperature will converge to the outside temperature, okay? So that's one way to go, but now I have the variable Q, which is embedded into my state X. The variation of Q during flows is 0, so it doesn't change because it's a logic variable. But every time that change occurs, the variable Q goes from 0 to 1 or from 1 to 0. And that law is essentially 1 minus Q, which is nice and linearly affine. And a logic that you could probably craft with some time to do that is to say, if I'm heating the room and the temperature is larger than my desired threshold, then turn off the temperature, turn off the heater, excuse me. And if the heater is off and the temperature is below some threshold, okay, no, let's turn on the heater. Right? So this essentially that you see right here, these objects build the jump set for my system, and these build my jump map. Okay. And then the complement of this, if you want it to be closed, you can close it, will be defining the flow set for my system. All right. And then you can imagine that you will have trajectories of this form where the temperature goes up, and then the logic variable changes and the temperature goes down, and the logic variable changes. Then you create a hybrid limit cycle of this form, which can be studied in the case of periodic switching, or a scheduled switching. It can be studied with Poincaré type of tools that we also have developed in some of our work. There is also the idea of conversion that I mentioned earlier. This is a different circuit. This corresponds to a circuit where you have amplification of the input voltage. You go from some voltage to a higher voltage. And the way that this works is very interesting. I like it very much because it shows how switches and hybrid play together. So you have a diode that you cannot control whether it's on and off. It's state dependent, but you have a switch here that you can turn on and off. So how does this work? Essentially what happens is when the switch is on, this power source feeds this inductor. So you essentially have a circuit here that is closed, right? And the inductor is collecting energy, it's storing all the energy. As soon as you open this switch, what's going to happen is that the inductor would like to continue having the same current that it had, and it's going to generate that current by creating plus minus voltage. So it's going to invert this voltage. And as soon as you invert the voltage of the inductor, what's going to happen is that this source plus this voltage generated by inductor will create higher voltage here. That turns on the diode, that loads the capacitor, and that loads the load, which is assumed to be resistive. What happens is that now I have the capability to switch in this switch S as I want, and I have multiple modes of operation of my circuit. And then what I would like to do, and I apologize that this is chopping off here, but what I would like to do, and this is probably good enough, is given a desired output voltage at the capacitor, which is assumed to be larger than the input voltage, and a steady state current that is reasonable for that voltage and is proportional to the load, I would like to figure out how to switch my switch to the transistor in order to create that voltage, almost approximately, okay? So I'll show you a little bit of how that works later on. I have many more examples, but I think this one would be very appealing to many of you because you're familiar with sample and hold control. So sample and hold control is a paradigm, or sample data system is a paradigm that uses essentially, in principle, periodic sampling and update of the input to the plan. So what happens is that there is a capital T time that every capital T, let's say the state of the plant, assume a state feedback, is going to be sampled. And then the input to the plant is going to be recomputed, and assume that that's given by some sort of a map. This could be proportional control if it was linear. Okay? So one way to actually encapsulate the mechanism sample and hold, which is again very prevalent, is to actually add a timer and then model the whole thing as a hybrid system. The timer can trigger the events, okay? And we assume for simplicity, but this can be extended, that sampling and actuating update occur at the same time. But again, this could be dissociated if you have a real DAC and ADC converter. So we can use an increasing timer that increases to capital T and then triggers an event, or we could have a decreasing timer that decreases to 0 and then triggers an event and is reset to capital T. Okay, let me take the former, which is simpler for now. I will say that this is probably even simpler of a hybrid system. And this is one of the examples I told in my class to think about on day one. I have a timer, tau dot is equal to 1, counts time, ordinary time forward. And timer tau is only allowed to evolve in 0 to capital T. As soon as it reaches capital T, because of the flow set of this model does not allow continued growth of the timer, what's happened is that if the evolution should continue, it has to be because of a jump. And that jump resets the timer to 0, and then it counts over again. And that's what type of trajectory that you get, okay? I will skip the negative one, but it's essentially another exercise. So with a positive count timer, what happens is that now I can write a closed loop system that incorporates the mechanism that triggers the events. In addition, what I realized is that because my model now will capture what happens in between events, in between samples, I not only characterize the intersample behavior, which is typically difficult to characterize, but now I need to have a memory state that will keep applying the input that I computed last to the plant, right? So with some abuse of notation, let me say that U now is a state variable, which is a memory state. And now I have the physical plant, the timer that triggers the event, and a memory state. So what's going on here? Z dot is evolving according to my dynamics, with U now being the memorized version of my input, feedback loop. The memory derivative is equal to 0 and doesn't change, and the timer counts forward time, okay? Whenever timer tau reaches capital T, because of this construction, there has to be a reset. What is the reset is going to do? Because of my definition of my jump map, what I'm going to do is to reset the timer to 0 so I can trigger another event capital T seconds later. The physics state does not change because it's a physical quantity, but my memory state is reset to the value of the feedback load that I should apply, okay? So that you see right here, and I'll show you what the Lyapunov function will look like for this, which you can design now for the full system without discretizing at all. You can actually design the capital T via Lyapunov conditions, defines the closed loop system, okay? Very interestingly, and one of the reasons we did this work is because now we would like to consider situations that are realistic, right? No system in the world triggers events at capital T periodically. There is always some sort of jitter. So how can we capture that? Well, what we can do as simple as enlarge the jump set, okay? That's your overlap. That's why we love overlaps. We don't mind non-uniqueness. And now instead of triggering events at capital T, we can trigger events at any point on the timer between capital T1 and capital T2. And let's say that these numbers are related like this, which is reasonable, okay? So I can now capture events or sample and call events, an actuation event that are separated as little as by T1 seconds or as large as T2 seconds, okay? And maybe I want to push that T2 second as high as I want, right? In order to characterize some sort of long delays that I can be compensating for. So models are there. We can spend the next 15 minutes or so on models. Let me tell a little bit about tools and then time for questions. But one of the things that we did to understand is asymptotic stability. How do we characterize asymptotic stability for this type of systems? First of all, because the models of the systems, closed loop plants or controllers might have more states than just the physics, we need to stabilize sets. Like for instance, for the sample and hold problem, we added memory, we added a timer. As long as the timer is between 0 and capital T, we are fine, but that leads to a set to stabilize, maybe for the physics component equal to 0. So we define stability for sets for hybrid systems, let me say asymptotic stability, by assuming or by requiring that the set is both stable, in other words, for every epsilon there exists a delta, such that if we start within delta, we remain within epsilon for all solutions, okay? So that gives Lyapunov stability. And then the other piece is the convergence part. We would like to have that if the solutions to the system exist for arbitrarily long time, and I mean hybrid time, either arbitrarily long T or arbitrarily long J, like in the bouncing ball, it will only happen for arbitrarily long J. Then if that happens, then I would like that the trajectories have a distance to the set that converges to 0, okay? The trajectory itself might not converge to anything because I might have a logic variable that keeps toggling between 0 and 1, but the distance to the set needs to converge to 0, okay? And in that case, we have the property of asymptotic stability. Now you notice that we have this term pre, and the term pre is actually telling us that there might be solutions to my system that die because of a deadlock. In other words, it might be, for instance, that the flow map hits a point in the flow set where flows are no longer possible. That's a bad design of the system, but our notion applies to such situations as well. From a plant, we would like to design a controller. So we typically, in control theory, we go in two ways. We try first maybe if luck is on our side, if we can get away with a static controller, right? Maybe output feedback and figure out whether there is a map, potentially nonlinear, that will, when we close the loop, when we plug this into here, this system, resulting closed loop system, is such that we can prove asymptotic stability of the set, right? And if that doesn't work, maybe we look for better certificates, let's say Lyapunov functions, or we look for better controllers, right? In either case, because in the dynamic controller, we can have an eta state, as I mentioned earlier, we will end up with some sort of a closed loop system of this form, okay? It turns out that, asymptotic stability in the pure definition, which I gave you, corresponds to, is for systems that are closed without inputs, okay? So I don't think there's reason to spend time on this. My slides will be available to you if you want to look at the details, but this is a mathematical definition of stability and attractivity in the pre-sense. But what is more important for me to tell you is that if we now want to guarantee that property, which is a solution-dependent property, without solving for the solutions to the system, what we can do is to use Lyapunov analysis, okay? So this is in our book in chapter 3 of our 2012 book with Andy Thiel and Rafael Goebel, where what you see here is that if we are given a set and a system without any properties of the maps and of the set whatsoever, if we can find a certificate, which we call a Lyapunov function, that is an indicator of the distance to the set, essentially is positive, definite, and radially unbounded. And very importantly, satisfies these two infinitesimal conditions, do not depend on solutions, which says that the variation of B, which is no more than the inner product between the degree and the directions of flow, is less or equal than some function that has a negative in front, but is positive definite, and is evaluated at the x to the distance of A, so this is what this quantity means, then this is saying that every time that there is flow, and that's only the points that I need to check this, I will have decrease during flows, okay, of this function B. And then similarly, if at every point in D and at every possible value after the jump of my state, I have that the variation of D is contracting or decreasing relative to the distance to the set to A, then I will have a contraction and B will decrease. What this is going to buy for us is essentially, and I skip a little bit ahead, is essentially that whenever I pick a solution to my system and I evaluate this function B, the Lyapunov function, what's going to happen is that this function is strictly decreasing, okay? Goes to 0. And if it goes to 0 because of the positive definiteness properties, we have convergence. We can apply this to the sample and hold problem, sample data problem, when the function, the right-hand side of the plant is linear, and when the controller that we start from is also linear. So we can design this K and design this T. And one way to do that we found convenient is to rewrite this system and insist that K and capital T are designed such that this matrix here, H, is a Schur matrix. In other words, satisfies the discrete time Lyapunov inequality, okay? So this is our design condition. And with this condition right here, what we can prove, and you can find the details on my slides, is that this set here, which corresponds to x1 equal to 0, x1 is the plant state, and my input will go to 0. The timer will keep oscillating between 0 and capital T. We can get the conditions for Lyapunov, the result that I mentioned earlier. One of the challenges is that these Lyapunov functions that are both decreasing in both regimes are hard to find. Again, I'm telling you the truth because I've seen it myself firsthand. And one thing that we typically end up doing is to find a Lyapunov function that decreases in one regime, but in the other regime does not decrease, right? Or the other way around. And sometimes it increases in one regime, but it decreases enough in the other regime, for which I need to know how long I'm going to be in each regime, right? So I need information about solutions, and that's essentially what we need to add to those infinitesimal type conditions. So how do we get that result? That is where sequential compactness is instrumental. We need assumptions now. So if we are looking at single value F and single value G, which is what I'm going to tell you, but there are cases where these are set value and we have conditions for that, which are just extension, all we need is that these two maps are continuous maps, okay? So bouncing ball was continuous, sample and hold was continuous, most likely this is going to be continuous. It is not continuous when you have friction. It is not continuous when you have rapid changes or nonlinearities like sine functions, and you can regularize and obtain an inclusion. And as I said earlier, we need these sets to be closed sets of the state space. Okay. So assuming that there is a version of these hybrid basic conditions for the set value case, which I want to spare you from, what we can do now is, first of all, is remove the dependency or the need to have a positive definite with a minus in front quantity right here by trading that with the set to stabilize be compact. Okay, so if the set to stabilize is compact, which covers a wide range of problems, certainly doesn't cover consensus, but there are a way around that, then we get that property, and we get with a weaker decrease. The weak decrease that we have for the flows is the following relaxed version that says, if I have less or equal, which is probably all I can get, weak, but if I have a strict decrease during jumps, which is this condition, then what I need to add is information about solutions, because all I know during flows is that it's less or equal than 0. So if there is a solution that always flows, right, which we call a continuous solution, then that solution is not going to exhibit along V this decrease, right? Therefore, it's not going to decrease. So what's going to happen is that we need to have persistency of jumps. So we need to have an arbitrary large number of jumps in each solution to my system. And that is essentially a property of solutions, which surprisingly, you can trade by properties of other Lyapunov functions. Like for instance, if you can prove that the jump set is finite time attractive globally, then there is always going to be a jump, right? And that finite time attractivity can be certified with infinitesimal conditions as well. So nothing is lost. And that was what happened for the bouncing ball. For instance, if you want to do this simple problem, you take the energy of the ball, potential plus kinetic. Certainly, since it is a conservative system during flows, you get that there is no decrease or no change of the energy during flows. But at jumps, because of the restitution coefficient plays a role, if that restitution coefficient is less than unity, then we're going to have a contraction at every jump. And because every solution to the bouncing ball is zero, there are infinite number of jumps, and you're done. You need to prove that it's zero, and there are infinitesimal conditions for that. There is a dual version of that. And then there is also the invariance principle related to this. If you have just weakness of decrease under the hybrid basic conditions, do not forget, what we have is that solutions that are bounded and exist forever can converge to a set that is invariant in the sense of LaSalle, Krasovsky, and Yoshizawa. With that, I'm going to skip a couple things, but we can further prove under the hybrid basic conditions is that there exists a Lyapunov function whenever we know that a closed system that is hybrid has a compact set, and the closed hybrid system has a hybrid basic conditions, and that compact set is asymptotically stable. And that buys us robustness. In other words, if we know that exists always a Lyapunov function that is strictly decreasing, then we can perturb a little bit the quantities, and we will all expect that things won't change too much. So that's where we get robustness from. Now, as I tried to do earlier, and hopefully the examples kept you a little bit engaged, there are many applications that require robustness, require stability, but also require other properties, like for instance, require safety. So this is one of the examples where we have this sign for a quadorder system that we can model mathematically as a physical system. We put it in our camera system, and now we design essentially a safety-based controller that will avoid all these threats that are being come to it. This is a project with NSF on cyber physical systems where we are assessing how fast can you do these computations in real time and implement the controllers. Safety is critical in most systems, and it's typically an upgrade from stability, an additional property that you would like to do once you guarantee stability. And it's essentially trying to find, the answer to what the reachable set is, which is, the reachable set is hard to compute. So this is the holy grail of safety, right? And one way to do this that is prevalent in the literature is to use what they call barrier functions, which are indicators of whether the state is in the unsafe set or not. Okay, so whenever it's positive in this context, I'm going to say that it's unsafe. Okay, have a couple minutes, and I just want to show you that whenever we can guarantee that the set of points where the barrier function is equal to 0 is forward invariant, and for hybrid systems, it will also be possible. Then what we can guarantee is that we have safety for the system. The question is, what are sufficient conditions, and maybe also necessary, but let's say, what are sufficient conditions to guarantee in forward invariance of a system? Okay, so there are many ways to do this. There are results in the literature that provide constructions for this. What we did is essentially find out a relationship between the monotonicity of the barrier function relative to the set, in other words, the non-increasing property of the barrier function along solutions, and safety. And what we can prove, and I have it right here for us to, okay, right here, is that we will have a set K defined as the zero sublevel set of the barrier function to be forward pre-invariant if we can show that this map, which is essentially the evaluation of the barrier along the solutions to the system, is not increasing, but only on a neighborhood outside the set that we want to render forward invariant. This is for continuous time systems, that extends to hybrid systems, but this is the building block. In other words, forward invariance or safety is a property that in general demands us to check what happens outside the set. It's not an internal property. It's almost saying, I have a bucket of water and I want to make sure that the water stays there. What do I look? Well, I can look inside if the water level is the same, or I can look outside if the water is coming out, right? So essentially what we do is to look at whether there are spilling out solutions, and that is necessary and sufficient for invariance and for safety. And we have done some work for these type of systems. One last thing that I wanted to mention, and then I will wrap it up, is that we were able to also extend from safety properties related to temporal logic. So what is temporal logic? Temporal logic is a property, or is a language that allows us to capture high level of specification. So essentially, eventually reach a target location and remain there for all time. These type of properties require essentially operators. And one of the more interesting operators are the two ones that are listed here. One is the eventually operator, and the other one is the always operator. Always can be handled with invariance or safety because it's essentially something always needs to occur. But eventually it's very challenging because it's essentially a property that says, in some time, I would like this property to be true. And that has to be finite time. It can't be in the limit. So most of the tools for stability from control theory gives you properties of that sort in the limit. And that doesn't really cut it here because we wanted to have a finite amount of time. So what we're able to show is that we can build certain sets that will allow us to guarantee attractivity in finite time for these systems to certify eventual type properties. Okay, we can also quantify how long it's going to take for that property to hold, as long as we can have a Lyapunov-like certificate for the system. Okay, some of the applications, which I didn't get into more detail, but I just want to show you some videos, use also predictive control and hybrid predictive control. These are the type of trajectories that in the context of the biped robot that I mentioned to you, you could think of generating. And there are other problems that I won't have too much time to tell you about, but happy to stay around and tell you more. Thank you for your attention. I hope that this introduction and overview of the work that we've been doing is useful to you. And let me just say thank you to the sponsors.
All right. Thank you very much, Ricardo, for this amazing, exciting journey from the starting building, let's say, an hybrid system model to the most advanced application to robotics and so on. And I'm seeing that you're also visiting Lucca, hopefully, soon. Okay, so there is probably some time for questions if the audience wants to raise their hands or just write down in the Q&A or the chat. Otherwise, I will have a lot, but I'll try to contain myself. And so just some curiosity or some clarification on your model. So there are these either corner cases or interesting cases in hybrid automata or in hybrid systems where the dynamics, the continuous dynamics might be stable, but it's because of the switching that the system becomes unstable, or vice versa, even systems that probably in their dynamics might have some unstable behaviors, and it's because of their switching instead that the overall hybrid system is actually stable. So I was wondering whether your Lyapunov functions actually are encompassing, useful in this setup, or are explaining, or the two different flavors of Lyapunov functions are actually addressing these issues, or?
Excellent question. I didn't get to that. You have a very good point. That's very useful in application. So what I'm showing you here is directly from our 2012 book on hybrid systems with Andy Till and Rafael Goebel. What you see right here is essentially the case that you're looking at. And we need to have a handle on the growth. Essentially, that's the message. So what's going on here? Apologize, this is just a compilation issue. This should be the other way around. But what happens here is that what I want is that my v dot to be less or equal than some constant time v. That constant can be positive, right? And that means that my v dot grows according to that rate. And then I need to have a change of v at jumps that is essentially controlled by this bound. So now I have these essentially couple inequalities that I can probably prove and maybe massage things. And in particular, we use this for event trigger control. In event trigger control, what happens is that during flows, we have a growth, right? Because our control law, almost like a sample and hold, is stale, right? And then every time that we reset, we have a nice contraction of some quantity. Okay, so you can imagine that this is less than than 1, and this is essentially positive, right? So we grow during flows, at jumps decrease. What we will need to do is an extra piece of work, which you need to prove, is that this lambda c times t and this lambda d times j can be upper bounded by something of this form, where now this gamma is a constant that is positive. Okay, so what happens is that as time evolves, at least I need to find a way to dominate the potential linear growth of my lambda c, which might be positive, by a lambda d that will need to be negative in order for this to be less than 1. Okay, so what happens is that there has to be some sort of, as I said earlier, information about the domains of how often I execute the contracting regime, right? In order to compensate for the non-contracting regime. Okay, so this is essentially the weakest result that we have, and we use it in maybe I can pull it off. We use it in event trigger control for let me find it here. I believe the paper is here already. Yeah, okay. So in this article on event trigger control, there it is. Okay, so see this, if we're using this result, this very result that I was mentioning here, 329, should be proposition, that I mentioned to you for the control of event trigger control algorithm, which maybe will be something we can discuss. But this HET is essentially the H that I mentioned to you today, but that emerges from doing event trigger control. So what is event trigger control in this framework? It's essentially a generalized version of sample data systems, right? Because now I don't have necessarily a time trigger, but I have a state-dependent trigger, which could be more than the timer, right? It could be the physical component of the system and so on. And that is instrumental. And what we're able to find is that we can, by doing that analysis based on, as you say, essentially a balancing argument, right? By doing that balancing argument, we can enlarge what is called the lower bound in between events, which is the most important contribution of event trigger control, which is sample less frequent, which I really like.
Yep. Yeah, and in fact, actually, it's a great message also to our students, right? Wow, how actually when people run a MATLAB, you were showing MATLAB also in earlier slides, right? And a simulation model and the solution. What is actually behind all that for just simulating also one of those models?
Right. Yeah, I haven't opened MATLAB this year, but let me just open it, and while other questions come up, I'll show you how this works really quickly. So I'll be happy to take other questions if there are any other questions.
Yeah, so yeah, I still invite the audience, otherwise I have one last one, which is a little bit more visionary, because even my team and so on, we are interested a lot in compositionality in systems. And it looks like also your framework with not just differential equation, but differential inclusions, right, might help in some kind of conditions, boundary condition between when composing systems and so on. But more broadly, I wanted to just ask you a perspective or on the state of the art in terms of, okay, there are hybrid automata there and probably input-output hybrid automata and so on in general, splitting system, decomposition, and building proofs, starting from inferring from components proofs, potentially, for instance, from stability and robustness. Can you infer anything about the safety of the overall system? That is also a pretty interesting application in cyber-physical systems.
No, that's a very, in my opinion, very fruitful direction. I mentioned to you that we've done some work on safety. Let me just mention it to you, point it to you here very quickly. And then I will answer your question. Okay, so this article that just appeared in Automatica provides sufficient conditions for invariance, which is essentially in the context of safety. And with what you were just exposed, you will be able to identify what's going on here. Essentially, we would like to find a function B, which we call a barrier function, that is only positive, strictly positive on the unsafe set, and is less or equal than 0, hopefully everywhere else, right? And that everywhere else is forward invariant, but that's typically not the case. But as you probably now are familiar, we want that barrier function, and forget about the I, we use multiple barrier functions, but we want that barrier function to be non-increasing during flows. As I said earlier, outside the set, we want to render invariant because inside requires a lot of regularity in order to say something about outside. And every time that there is a jump, we would like that barrier function to go back to being less or equal than 0, because less or equal than 0 is the safe condition. These results, and these are all infinitesimal, doesn't involve any solution. These results are for closed systems without any input because they're closed, and they're not compositionally in nature. What I'm very interested in, and I think is a very important direction, is how can we use, in my opinion, these are the weakest conditions we ever seen for even continuous time systems for forward invariance and safety. How can we now compose systems that I would like them to be safe when I compose? Maybe I start with some sort of input to state safety, right? Because the input is unassigned. So as long as the input is okay, I'm going to be able to get safety, let's say. How can I show now that I can compose them and show safety of the full system? So I really like that. One needs to deal with the fact that cyber-physical systems, if each of these subsystems is a piece of a cyber-physical system, will have its own physics and its own logic. So you will have its own events, its own dynamics. And when you compose them, how do we know that the certificate for one system and the certificate for the other system will lead to a certificate for the whole system? Let's just consider, let's say, a series interconnection to start, or a feedback interconnection to start. Those questions are, from what I've seen for CPS in general, are open. And there's a lot of work to be done there.
Yeah, and yeah, probably also offline. I'll probably ask more on pointers on where the state of the art is also standing, and we can probably chat more. I would have lots of more questions as well. Okay, but I want to steal more time. So if there are other questions, so if you want to actually show us about MATLAB.
Yeah, 1 second, right? So you download this tool from MATLAB Central, that's where it's hosted. And there are a bunch of examples. One of them is the bouncing ball. And here you have one that we crafted with a very valid step size so that the user needs to find a way around it. But anyhow, what happens here is, if I can open this, yeah. So the tool that we developed is essentially an equivalent to, let's say, OD45, OD113 calls, right? Essentially what you need to do now to run this tool, once you download it and install it, is to pick the initial condition of your system, right? To pick the simulation horizon, which now is hybrid, certain amount of T, certain amount of J. Let's skip this for a second, and then run the solver, for which you need to pass the flow map, the jump map, the flow set, and the jump set, okay? And then the result, if everything goes fine, is something like what I was showing you here, is these nice trajectories of the bouncing ball, right? Or whatever system you're simulating. How do you call the flow map? Well, it's just the evaluation of the function. So essentially, the output of that function should be the function itself value, x2. In this case, gamma is minus the gamma use. Apologize, but it's just the function, right? Jump map is x1 with a minus because of computation errors, minus lambda times x2. And then the jump set, let's say, is output in 1 if the state is in the jump set, and output in 0 if it's not in the jump set. As simple as that. And the C is whatever it should be. So you run this tool, and then if you look into the tool itself, into this script, which is open source, you can understand how we parse the events, how we deal with non-determinism, right? If the state of the system is in both the flow set and the jump set, we need to make a choice, right? We need to pick which solution we want to approximate. And this is where the rule parameter plays a role, right? We're going to put some semantics onto this. We're going to pick a particular forcing semantics or enabling semantics or whatnot. And it's very intuitive. And when the students take my course or get exposed to my material, I find that this is a type of tool that is very useful. And then it could be used for things like reachability analysis, model predictive control, which we're also working on. I didn't get a chance to show you that, and model checking and things of that sort, that if there is interest, I'd be happy to discuss.
Yeah, absolutely. And yeah, and some of the problems inside indeed touch, yeah, very soon philosophy, like the representation of time and this idea indeed of infinite jumps or jumps at the same with the same time label and so on. All right, awesome. So thanks a lot for this journey, and yeah, so hopefully we will have you also in person when we get some normal conditions, and be happy to host many of our speakers actually in person that we cannot afford right now to have with us. All right, so with that, I want to thank you again, Ricardo, and give the appointment to all of you to our next Wednesday, our next seminar. So thank you all. Thank you, Ricardo, for joining us.
Thank you very much.
Bye.
Bye-bye.